I'd like to take this brief video just to show you how we can actually see linear regression as an orthogonal projection. Now, we're used to seeing linear regression, well, probably first as one equation, right? We have y equals beta naught plus beta 1 x1, however many variables we have. Here, I assume we have p variables. Now, this can be represented by a matrix vector product where usually called our design matrix X, which is just our data matrix having one row for every observation with an additional column of ones to include the intercept. So we have our design matrix times our vector of coefficients is equal to our observed responses y. Now, just to make this completely clear, when I have x1 in this equation, really that's in reference to this entire column of our data or design matrix X. So moving on, I can again represent x beta equals y as my system of equations for regression. And my question to you is the vector y in the span of the columns of X? Well, a translation of this question is just, is there an exact solution for beta? Because you'll recall the span of the columns of X is the set of all linear combinations of those vectors in X. So what I'm saying is, can I find a beta 0, beta 1, and up to beta p so that I can make this an exact equation? And the answer is no. That's why we use least squares, because this system of equations up here is inconsistent. It has no exact solution. Our data does not fall on a flat line or planar surface. So the objective in regression is to find the point, we call it y hat, that is contained in the span of X and minimizes the squared error. Now, one way to represent the squared error is as the norm of y minus y hat. Remember, this is the square root sum of squares. So I've taken the square root, but obviously if I minimize the square root, I minimize the square. And again, I can translate that objective to say that we want to find the closest point, y hat, closest in the Euclidean sense. The Euclidean sense is just our normal sense of distance, that sum of squares. So find the closest point, y hat, that is contained in the span of X. Well, let's consider this geometrically for a second. Now, the span of X, I'm not sure exactly what that looks like because I have p variables. And so that design matrix X has p plus 1 columns. But I do know that when I take the span of a set of vectors, I get a subspace. And if you'll recall, in an earlier video, I told you anytime you're thinking about a subspace from a higher dimensional space, it will never hurt to keep this idea in mind of just using a plane to represent the subspace inside of a three-dimensional space. So let's let this plane here, this green plane I've drawn, represent the span of X, the span of the columns of X, that means. And now I have Y. Sadly, the point Y, that response variable, is not contained in the span of X because I don't have an exact solution. Well, if Y hat is the closest point to Y that's contained in the span of X, well, it's got to be the projection, the orthogonal projection of Y onto the span of X. And it is. And this distance between those points is that sum of squared error, the square root sum of squared error. It's the distance between Y and Y hat. So therefore, you can actually think of the vector epsilon, that vector of residuals, as its own vector in this space. And y is equal to y hat plus epsilon. Again, when we add vectors, we add them tail to head. So I think overall, students can grasp this concept, but when they really start thinking about the span of X, they start to confuse themselves again. And I understand that. It's taken me a long time to get to a level of comfort with this, that it's second nature. The fine print here is that the span of X is a p+1 dimensional subspace of Rn. p+1 because I have p variables plus the intercept. So if you think of those columns of X as forming a basis in some way, that means I have p+1 basis vectors, so that the span of those basis vectors is a p+1 dimensional subspace. And each of those vectors lives in Rn, where n is the number of observations. Right? Every column of X lives in Rn because it has n elements, one for each observation. So Rn, in this case, the ambient space that the span of X lives in, is what I would call the sample space, or the sample vector space, which has an axis for each observation. It is very uncommon for us to think about our data in this way. Think about the columns of X, each variable plotted in space. But it can be helpful moving forward in certain situations when we're trying to work out some of the geometric implications of what we're learning. So if you can wrap your head around that, it's great. If you can't, that's okay too. At some point, you may find it clicking into place. So the last thing I want to talk about today is the projection matrix. And it turns out there is a formula for a matrix called the projection matrix that will give you the projection of any point onto the span of a set of columns. So if you have any matrix X and you want to project a point onto the span of those columns, you would multiply by the projection matrix, usually written as P sub X and defined as X times X transpose X inverse times X transpose. Now, you may have seen this come up in your previous statistics classes. It's often referred to as the hat matrix in statistics because it puts the hat on Y, meaning that when you multiply it by Y, you get Y hat. And of course, inside of this equation, we have the formula for beta hat, because again, our whole system of equations becomes X times beta hat equals Y hat. That was fun. Major ideas from this section that we've covered are the cosine and angle between vectors, orthonormality, an orthonormal basis, orthogonal matrices, and orthogonal projections. Have a good one.